It is now moving on to the next part of our session. I would like to bring up Eric Drager from the Lawrence Livermore National Laboratory. I got there. That's a lot of L's. He is our posters, a member of our posters committee, and has been very willing to serve, and I appreciate that, Eric. Thank you so much.
Can people hear me? Yes, good. So this is the most nerve-wracking session of the conference. Luckily not for me. We're going to watch a heroic display, and I will explain in a moment. So tomorrow is our poster session and reception. We're not doing it right now because we only have 20 minutes, but we are going to whet your appetite and give you things to think about ahead of that. And not only should you go to that to hear and talk to all the amazing poster presenters, but there's also will be a reception, so you should do that. But most importantly is you get to actually choose the best poster. This is going to be a voting process. You'll get a little card. And of course, you can make people, dance for your vote. So it's fun for everybody. We're not going to have time to get through the institutions behind these posters. So we just want to put up the panorama of them. There's quite a few. It fits on 2 slides. And now we get to the actual business, which is each poster presenter has exactly 30 seconds to give you a little pitch for why you should come listen to their poster. And just tonight in your hotel room, try doing this. I tried it when they asked me to do this, and it was a disaster. I was 15 seconds, and then I was like 2.5 minutes. So God bless these people. The way it's going to work in practice, I was hoping to have like an air horn or something, but actually it's much more humane. There's going to be a little counter. When the counter is done, the little pie chart is over, I will flip to the next slide. So you have the full 30 seconds when the timer starts. You don't need to tell us your name or your poster title. I will read those. That's time you can spend telling people the story, but let's kick it off. Our first poster, Accelerating the Computation of Koopmans Functionals Using the SIRIUS Library. Our presenter is Giovanni Consalvo Cistaro. And when he is in the middle, I will hit the button. All right, take it away.
Hi all. So Koopmans functional are some tools in the FT community, so in condensed matter community, that are used to calculate and predict correctly spectral properties in materials, but they are very demanding. So what we did is to port the main functionalities in GPUs. More importantly, our porting can work on both AMD and in NVIDIA GPU, and here you see one of the problems that we solved in GPU. There is a linear system with very huge dimension in the order from 1,000 to 100,000. So come to my poster to have more information. Thank you.
I think I may have been more stressed than he was because I still am upset by this whole process. All right, our next poster is Accurate Machine Learning Force Fields via Experimental and Simulation Data Fusion. And our presenter is Sebastien Röcken. Start talking and I'll hit the button.
In molecular dynamics, machine learning force fields enable fast and accurate simulations. They can be trained either bottom-up on accurate simulation data or top-down on experimental targets. Bottom-up models often fail to reproduce the experimental targets, while top-down models often fail to reproduce out-of-target distributions. Our poster presents a fused bottom-up and top-down learning approach, which simultaneously satisfies experimental targets and out-of-target distributions. If you want to know more, I'm happy to see you tomorrow at the poster session. Thanks.
Nice. All right, number 3 is Additively Preconditioned Trust Region Strategies for Machine Learning. Presenter is Cruz.
All right. Hi there. So neural networks are becoming more expensive to train, such as large language models. We have employed a domain decomposition method called the Additively Preconditioned Trust Region Strategy in the data parallel, model parallel, and pipelining setting. So if you are interested in this, or if you have any pointers to give us, we welcome you in P03. Thank you.
Nice. All right, now poster number 4, Advancing Fault Tolerance in Graph Processing Engines Based on Total Order Multicast by Ekkehard Steinmacher.
Thank you. So Apache Kafka is an event streaming platform that guarantees total order within a partition. In this project, we expand the Apache Kafka framework to also provide total order across partitions. And we do so by implement the separate hierarchical ordering scheme that determines when messages are actually delivered. If you're interested in how the scheme works and also how it performs, please swing by at PO4.
Nice. Our next poster, Advancing Flood Simulations with Triton, a multi-GPU 2D hydrodynamic modeling code. And our presenter is Mario Morales Hernandez. Never mind. P6, Atlas as a unified data structure interface for computation on heterogeneous architectures. Slavko Brdar.
Yeah. Yes, thank you. So Atlas is the ECMWF C++ library with a Fortran interface for data structures and numerical methods. It's used by the IFS model. Here in this work, we are looking at GPU offloading strategies for Atlas. And if you want to see how we stack up against Field API, which is a take-on GPU offloading by Metro of France, you can join me at P06.
Thank you. Nice. You're all much better at this than I am, which makes me feel bad. Automatic generation of block-structured grids on complex ocean domains for high-performance simulation by Jonathan Schmalfuß.
Okay. Coastal ocean simulations are often done on unstructured grids by this point. This is the practical industry standard. Unfortunately, they suffer from cache misses often because we have, well, relatively we have problems with our stencils, and one of the solutions for this could be block-structured grids, where each block in itself is a structured grid, and the blocks are connected in an unstructured topological sense. They represent different varieties of the current status of our block-structured grid technology and perform, also show simulation results. If you want to know more about that, come visit me at 07.
Fantastic. Thank you. Okay, I think we have it working again. Next poster is complete asynchronous task-based implementation of a particle and cell code, performance studies and benchmark by Juan Jose Silva Cuevas.
Yeah, we had a data full particle inset method. That means with all the different sections of a classical particle and set, we had that to the paradigm of Taste Basic. We did through the backends OpenMP and Eventify, which is currently developed at the Jülich Supercomputer Center. And we present the main modifications that we did to the algorithm to erase all the synchronization stages and to favorize the task systems. Our earlier results shows a gain in performance in the case of a high unbalanced workload. So if you're more interested to know about the modifications that we did and our results, please visit our poster.
Excellent, thank you. Poster 10 is controlling parallel CFD simulations with Julia from C, C++, and Fortran programs of libtrixie. Presenter is Benedict Gehi.
Okay, good evening, everyone. So say you have your domain science code, that's the dragon up there. It's mighty, it's massive, it has always been around, but it's sometimes really hard to make it switch directions. So if you want to try something new, some cool stuff all your colleagues are always talking about, then we are here to help. We present libtrixie, which is a blueprint for connecting state-of-the-art modern software written in the Julia language to legacy HPC codes. So I hope to see you around, just beware of the dragon, and the bullets will also be nicer on the real poster. Thanks.
Thank you. All right, poster 11 is the Coulomb perturbed fragmentation CPF method, and our presenter is Fazale Sadat Kazemian.
Hello, everyone. In a simple term, our method CPF is combining both classical and quantum computing techniques to make energy calculation of the large molecular systems more accurate and efficient. we are using restricted Hartree-Fock methods as an approximation to Schrödinger equations, and also we are using many GPU systems to run expensive calculation and multi-layers workload distributions and 3 different MPI communication methods to make the most of the supercomputers. So if you had any question and you're curious how we are doing this, ask me your question.
All right, poster 12 is Ekkehard, a multidimensional probabilistic model for the deconvolution of heterogeneous transcriptic samples. Bastien Chassagnol.
So hi everyone, I'm Bastien Chassagnol, freshly graduated from a PhD in applied statistics and maybe looking for a postdoc in computational biology. And what I'm going to introduce you is a deconvolution algorithm. So deconvolution is usually known as a promising solution to the cocktail party problem, which refers to the difficulty of isolating the direct interaction with your interlocutor in your noisy and crowded environment. It turns out that we have to deal with similar issues with biological practical use cases. So if you want to know more about deconvolution, how it can apply to a variety of biological applications and what are the specificities of my model, then I can invite you to my poster session P12. Thank you.
Well done. All right, our poster is actually Dynograph, Learning Hidden Relationships in Dynamic Graphs. Lekha Patel.
Yeah, so this work is about learning hidden relationships in dynamic graphs. So dynamic graphs come across everywhere in complex science. And what our work aims to do is really to learn hidden relationships in these graphs. So for example, this might come up in biological pathways or climate interactions that we want to probe and learn more about. This is very preliminary work, so we're using kind of statistical learning or statistical machine learning techniques to be able to do so. If you're interested, come to P14, and if you have any ideas on how we scale this to large graphs using HPC, that will also be great. Thank you.
Nice. Our next poster is Enabling Message-Driven Architecture Evaluation for the Extreme Heterogeneity Era with Mosaic, and it's Patricia Gonzalez-Guerrero.
Thank you. So to solve the pressing issues that we all care about in scientific computing, we need more power, more performance, more in computing. And we know that we haven't been able to deliver more and more performance, unfortunately, because we are hitting limitations in scaling up, in power consumption, in transistor size. So when we hit this blockage, we know that nature has a way to deal with this scarcity problems, and it's by specialization. So if you guys are interested in my poster, I'm going to talk about how we can use specialization for high performance computing. How can we integrate the knowledge of scientific experts to impact what we do in the hardware architectures that we use for HPC.
I was actually supposed to tackle the people who went over, but I didn't have the nerve. Poster 16 is Enhancing Aerosol Predictions on the Global Scale with Particle Resolved Modeling and Machine Learning, and that's Nicole Reamer.
Yeah, hi everyone. Our topic is related to climate and aerosol cloud interactions. So these processes introduce large uncertainties in our current climate simulations. And we tackle this problem with a combined approach consisting of a detailed model that simulates the transformation of individual particles in the atmosphere and machine learning. And we present 2 applications in this poster. And so if you want to know more about these applications, come and see me at my poster.
Nice, thank you. I'm going to skip P17 because it's not here apparently and go straight to P18, my first success. Exact conservation laws for neural network integrators of dynamical systems, and it's Eike Mueller.
Okay, so I think you should have a look at my poster because it fits squarely with the conference theme of combining physics and modern machine learning. So the problem we are trying to address is learning the dynamics of physical systems from data. So that's a bit like looking through a telescope at planets and inferring the laws of celestial motion. But we want to do this in a way that incorporates crucial conservation laws, such as angular momentum conservation. And to do this, we combine a very deep theorem from theoretical physics with modern methods of machine learning.
Well done. Thank you so much. And our final flash presentation for tonight is Fast and Scalable Algorithms for Selected Matrix Inversions by Lisa Gadek-Mershauer.
Thank you. So, as you might know, the inversion of sparse matrices will give rise to dense systems. And so for high-dimensional problems, this becomes very quickly an infeasible operation. However, for some applications, you're only interested in selected entries of the inverse. And so we've taken advantage of this characteristic and developed customized algorithms to perform these so-called selected matrix inversions. And we put forward GPU-accelerated as well as distributed memory implementations. And in our poster, we showcase their application to problems in the field of Bayesian statistics as well as quantum transport. And so you're very welcome to come by and have a look.
Thank you. And let's just give one more quick round of applause to all of them, because that was terrifying.